Hi, uh, today we're going to be talking about the statistics and what a statistics is and what is our objective in our course to learn about statistics. First of all, statistics is a science. It is a science about data. That data could be values, numerical values, measurements, numerical measurements. They could be counts. It could also be something that doesn't have a numerical value. We divide statistics into two types of statistics. Descriptive statistics, which we are going to spend some time talking about, and inferential statistics. Now, the difference between these two is that descriptive statistics is mostly about collecting, organizing data, presenting the data, methods of collections, methods of organization, uh, and methods of presentations. Inferential statistics would be about analyzing the data that you collected. And also, it would be very important to be able to make some conclusion or inferences from that data. Data is collected in a sample from a population. So the population is not necessarily anything living and breathing, but rather a set of numbers, like, for example, the heights of 18-year-old males in the United States. So I would have all of the possible numbers. Let's talk about inches. So somebody that is 70 inches tall, somebody that is 67 inches tall, somebody that is 71 inches tall, somebody that is 70 inches tall, not necessarily different, all of them, right? Of course, they're not. Somebody that is 65 inches tall, somebody that is 57 inches tall, somebody that is 75 inches tall, and on you go. You can have lots of different things, and it would probably be in counts of hundreds of thousands. So there are many more numbers here in this population. If we collect just a portion of it, we call that a sample. So sample is generally just a portion of a population. The variables could be independent and or dependent. That could be something that is related to something else. For example, the height of 18-year-old male and the shoe size of 18-year-old male would be dependent variable because there is a association. If you are taller, you'll likely have bigger shoes and so on. They could also be discrete. If you can count the values, then they are discrete. If you cannot count, if it's just measurement, something that you measure, then it comes in ranges. So it's usually approximation. That's exactly what the height is. It's approximation. Nobody is really 70 inches tall. It's something close to that, right? So those are something we call continuous variable. Now, variable itself is a description. So when I say a height of 18-year-old male in the United States, that's a description of these numbers that I have in the population. So that description we call a variable. It could be something else, a shoe size of a random 18-year-old male in the United States, or a mileage per gallon of a random four-door sedan that is currently on the road in the United States. So as you see, it could be a rather long description, but that description is what we call variable. Now, when we collect samples, so something that is a portion of the population, we will get usually relatively large set, but much smaller than is a population. Population is usually significantly larger. We could collect that data, as we call instances. Every particular number that we collect is an instance of that variable we are interested in. Maybe a mileage per gallon of a four-door sedan on the road in United States. One number like that would be an instance of that variable. We collect that by using observation, which is not necessarily just by looking at something. It could be a lot more work. For example, if I need to find out the mileage per gallon of four-door sedans on the road in the United States, I might want to go to Walmart parking lot, particular Walmart parking lot like Comac Commons. There, I would have to identify the model of a car in a parking lot. If it's a four-door sedan, I would probably have to use some book that gives me a description of the car so I can recognize what the car is. Then I would go home. I would be looking on the internet, government website, fuelefficiency.government, where I could actually find the mileage per gallon of that vehicle. And that would be done for every single car that I would find in the parking lot that would be four-door sedan. So it's not something just by observation. That's a lot of work involved. We could also collect the data by using experiment. Experiment is when the one who is collecting the data has a direct impact on the data, meaning there will be some changes in the data because of the person who is collecting data. So for example, we do that when we are testing growth of a tumor in mice. So I would probably inject mice with some genetic material that would create a tumor, and then we would measure that growth of that tumor. The growth of the tumor, of course, is not natural. Something that happened in the mice. It happened because we induced that. Or testing drug effectiveness, in which case we probably would have two samples, one when we were giving people drug, and the other one when we are giving them something deceptive, like we call that placebo, like a sugar pill, and then we would compare the two groups. So on the first group that receives actual drug, and we call that kind of group experimental group, we have a direct impact. On the second group, we might not have an impact. That group is called control group, other than by psychological. So there is a certain level of psychological impact. So that, again, is the data collected by experiment. We probably want to compare, but difference between experiment and observation is that in the case of experiment, we have the one who collects the data, supposedly us. We would have direct impact on the values that we are collecting. Then you could also make a simulation, collecting data by way of simulation. That is in case when there is something too expensive or too dangerous to do by observation. So, for example, 1 megaton nuclear attack is something that we would certainly not be able to create realistic situation. We could not nuke anything. Then we would probably make a simulation by using a computer program, and then we would collect the data based on the results of that computer program. That would have to take into account many different things that would happen in realistic situation, as in climate, topography, the density of the population, and so on. We could also collect it. So the main difference here is that the data collected by simulation is virtual, it's not real. We could also collect the data by way of census, which means complete collection of all of the population data. Now that is usually impossible. Sometimes Sometimes it is possible. When we are collecting SAT scores, there is a company in New Jersey, Educational Testing Services, and they have all of SAT scores. So we can have all of the SAT scores rather than having just a portion of it. But sometimes it's not possible, and the government does spend a large amount of money to collect the data that is very difficult to collect otherwise. And they do that every 10 years by the way of census, national census. So they collect various different things that they are interested in. For example, how long you have to commute to work and things like that. They don't get 100% of the population. They get maybe 80%, maybe 90% of the population. But that is still called a census. So census is when you're collecting the data that is very close to the size of the population. Sample is very close to the size of the population. No matter how good your sample is, the sample will always have something we call sample bias. Bias is defect of a sample that tells you that the sample is not exactly a representative of the population. There is something in that sample that makes it slightly different than what you would expect in a population. We try to make it as close to a representative of the population as possible, but in general we will always end up with some bias. We can actually in statistics measure that bias. That bias could be numerically measured, and there is a way to do that, but this is not going to be a topic of our course. Okay, when data is collected, the data might have different level of measurements. Some of the data is only of a nominal level of measurements, means it has only nominal value. For example, color, gender, zip code. A zip code actually comes as a numerical value, but it doesn't really have any numerical meaning. For example, 11717, which is a zip code of Brentwood, does not have any numerical value in terms of anything valuable to us as a number. It's just a geographical location that is labeled with that number. So this type of data is very often, but it's not as often as numerical data. Now, the first level of measurement that is a numerical level of measurement is ordinal level of measurement. You can see that very often in customer satisfaction surveys. Grade is something like that. So for example, in customer satisfaction survey, you might have to select numbers in which you are going to express your satisfaction as a customer, and one would be like a poor service, 2 would be satisfactory service, 3 would be good service, 4 would be very good service, and 5 would be excellent service. These numbers are only important in terms of comparison between them. So I can say that 5, customer satisfaction of 5, is better than customer satisfaction of 4. But I cannot tell you that is 20% better or 30% better or anything like that. I just know that it is better. So I might as well also use non-numerical values, A, B, C, D, and E, or 10, I could use a different numerical value, 10, 20, 30, 40, and 50, and sometimes people do that. Again, the numbers are only comparable. They do not have the numerical value itself compared to the other numerical value makes sense, but numerical value itself doesn't. For example, if you think about it, what would 5 represent as an excellent service? You could not come up with anything about it. You could just say, well, it's better than 4. Then the next level of measurement, the better, more comparable, would be interval level of measurement. You can, for example, talk about outdoor temperature. Now you have perhaps 40 degrees, talking about Fahrenheit, right? 40 degrees Fahrenheit, that would be uh, relatively cold. Then you have 60 degrees Fahrenheit, that would be relatively okay, I guess, for walking. And you can have 65 degrees of Fahrenheit, which would be a little nicer and probably a nice day to walk around, right? So what I know here is that 65 is better than 60 and 60 is better than 40 in terms of how I feel outside, right? But I also know that 65 is not that much better than 60, but 60 is significantly better than 40, meaning that this interval between two numbers, which is here 20, and in this particular case is only 5, it also tells me something. So the numerical values are, the interval between two numerical values is also telling me something about those numbers. It's not just comparison which number is bigger and which one is smaller. We also have the best possible level of measurement would be, or the highest level of measurement would be ratio level of measurement. This is when you can actually make comparison based on ratios. So for example, wage. If we are talking about a wage, if somebody has 100,000 annual income and another person has, let's say, $60,000 annual income, you can divide these two numbers in either way you like. You can divide the bigger one with the smaller one, or the smaller one with the bigger one. If you divide the bigger one with the smaller one, you are going to have, you can lots of cancellation here. You're going to end up with 5/3. And that would be approximately, let's just do the approximation here with a floating point number, 1.67. And we could say that this person with $100,000 annual income has a 67% higher income than the person with a $60,000 income, which means you can compare these two numbers, and that will give you another meaning of the comparison between these two numbers. You cannot do that with the temperature, because you could also have a 0, for example. If you divide 60 with 0, it will give you no result. You cannot divide with 0, right? Or if you divide 0 with 60, you got 0. What is the meaning of that? Doesn't have any meaning, right? Or if you divide negative temperature with positive temperature, or vice versa, you get a negative number, and again, you really don't have any meaning to that number. So the temperature, the outdoor temperature, could not have ratio level of measurement, but the income would have that. So if you're dividing two numbers, you can actually say, you can divide 60,000 with 100,000, and you could say that 60,000 is 40% less than 100,000, right? So that would tell you. You can compare that either by saying that the higher income is 67% higher, or you can say the lower income, if you divide 60,000 with 100,000, is 40% lower income. So that's the best, the highest level of measurement you have. Again, in a particular situation, of course, you will collect what is possible to collect. So if we're talking about outdoor temperature, I cannot make that into ratio level of measurement. I will just have an interval level of measurement. If I'm interested in collecting an information about the gender of people, like my students, I can't turn that into a number. I can possibly write it as number 1 or 2 or 3, but it would have no meaning, like a zip code, right? 1 for male, 2 for female, 3 for transgender or something else. I don't know what else we could have, but it would not have meaningful numerical value. So in that particular case, you just collect what you are able to. Okay. Now, if you are collecting a sample, what you're trying to do is to have a sample that is representative of the population. But I already said that no matter how you collect a sample, there will always be a bias in that sample. It's an intrinsic defect of a sample, right? So we have two things here. We have a methodology of collecting a sample and the ultimate result. So you have to be aware of the difference here. Methodology of collecting a sample could be perfect. We could have a methodology to collect what we call simple random sample, the best possible way of collecting something that should be the closest as a representative population. That's a methodology. Now our methodology here would be by a way of lottery. What you're going to get at the end, it's not necessarily going to be perfect in terms of what is the representative population. For example, if you are drawing numbers between 1 and 40, like in some lottery situation, or 1 and 99, you could end up, no matter how nice you organize that, you could end up with 1, 1, 1, 1, 1, 1, 1, 7 ones. So it's going to be random selection, so that could happen. So that end result, your sample of 7 numbers out of those 100 numbers, is not perfect. It's not representative of those numbers. You certainly have 2-digit numbers, you have even numbers, and so on, and none of your numbers is even or 2-digit, right? So that's the problem. So the sample itself had to be distinguished from the methodology of collecting a sample. So when we say that we are having a simple random sample, we are really talking about methodology. Okay, at the end is going to be a sample, but we are talking about methodology. So to give you an example, if I am a commander of a battalion of 900 soldiers and I need to select 300 of them for a dangerous rescue mission, I could do a simple lottery business out of that. I'm going to write every single soldier's name on a piece of paper, identifiable, right? So 2 soldiers have to be 2 different things. I will put that in a box, and I will do a drawing from that box blindly. So I'll take one, and then second one, and third one, and so on until I reach 300. That is a methodology that will give me what we call a simple random sample. What is a simple random sample theoretically? It has to satisfy the following. Every single soldier, every single item from the population has to have the same chance to be in your sample as any other item in the population. Any 2 items in the population have to have the same chance to be in your sample as any other 2. Any 3 have to have the same chance to be in your sample as any other 3. And on you go. Any 300 have to be with the same chance to be in your sample as any other 300. The lottery as a methodology would provide me with that. I would have exactly that what I stated. Okay? Now, let me tell you about something we call systematic random sample. The way we collect random sample in a systematic fashion that looks almost perfect, but it's not quite. Now, this could be done in the following manner. I would have a 6-sided die. 6-sided die, of course, it has 6 sides. And on one side on that die would be 1. On one side it would be 2. On one side it would be 3. On one side 4. On one side 5. On one side 6. So I have this 900 soldiers, so I'm still uh, trying to select 300 soldiers from that battalion of 900. So I have 900 soldiers and I have a roll with their names in alphabetic order. Number 1, number 2, number 3, and so on. I'm just gonna roll this die and it will turn out to be either 1 or 2 or 3 or 4 or 5 or 6. If it's 1 or 2, I would select the first soldier in my roll. If it's 3 or 4, I would select the second soldier in my roll. If it's 5 or 6, I would select the third soldier on my roll. Okay, you have to agree this is somewhat unbiased in a selection of a single soldier. They all have equal chance, 1 out of 3, to be in the eventual selection. The number 1, number 2, or number 3. Okay, if number 1 is selected, then I will take every third after that. The number 4, the number 7, the number 10, and on you go. And that way I would reach 300. If number 2 is selected, I would take number 5, number 8, number 11, and on you go. If number 3 is selected, then I would take the 6th and 9th and number 12, and on you go. Okay? So you can say, well, this looks quite unbiased. Yes, in terms of a single soldier. They all have the same chance to happen to be in your sample as any other soldier. However, 1, 2, and 3 could not be in your sample. Yet 1, 4, and 7 could be in your sample. So when you look at those 3, 1, 2, and 3, one of them will be in your sample, in your selection, but not all of them. While 1, 4, and 7 will be in your sample with a chance of 1 out of 3. Because if the die ends up as 1 or 2, you will have 1, 4, and 7 in your selection. So you see, we are violating the basic principle of simple random sample. Right? We are violating the being unbiased in terms of alphabet. There is no way that you can select 2 consecutive people in the alphabetic order here. Right? So it looks like it's very unbiased, but actually it isn't simple random sample. So it's a little bit less perfect, but it's much easier to do because all you have to do is to roll a die once, and then you just immediately select everybody from the roll. While in this first case, you need to actually write all of the names, put it in the box, and draw 300 of them. That's a significantly more work. But this way of lottery is actually a methodology that is the best methodology you could use. While this one here, while it's easier, is not the best one. So people usually have, my students, usually have the problem of distinguishing between the two. Systematic random sample is you select somebody in that sample in the beginning, or in the population, excuse me, in the population, somebody in the beginning, if you have some kind of sorted population, and then after that proportionally you take, in case you're taking a third of the population, every third, in case you're taking a tenth of population, every tenth, and so on. And you will always end up with what you wanted, but it isn't going to be a simple random sample. It is what we call a systematic random sample. Next, the best thing to simple random sample. You could also select something that we call stratify random sample. Okay, now sometimes we have problems when we are doing simple random sampling that we want to avoid because there might be some bias that is a little more important than another bias. For example, if I'm looking for a political opinion or opinion about a certain political candidate, I am not interested in looking for for being unbiased in terms of a shoe size. I don't care about it, right? Because I don't think that political opinion is connected with the shoe size. But I do think that political opinion is connected to the gender. And we know that from the previous election that the male and females are voting differently. So, or age, or income level, or something else, religious affiliation, for example. So people have certain factors in their thinking that are going to be associated with their political opinion. So if we want to collect something from a population that will resemble to a population, we want to avoid to collect mostly males or mostly females. We don't want to collect mostly older people or mostly younger people. In that case, I'm not really all that interested about simple random sample. I am more interested in stratification. What does that mean? It means that before I collect anything, I'm going to divide the population into stratas. That is layers. I will divide the population into stratas, and then I'm gonna take proportionally from that strata. So if I had an information in the past that we have 48% of the voting population are males and 52% are females, I want to have in my sample 52% females and 48% males. So I'm not gonna just collect that at random from a population. I will first divide population into females and males, and I'm gonna say, if I wanna have 100 people, 52 must be females, 48 must be males, because I know that in the last election that was the distribution of gender. And I would do the same thing with age. If there is a 35% of the people that are voting 55 or older, then I need to have in my sample 35% in the sample that are 55 or older. So that's called stratification. Or in this particular example, if we are talking about a battalion, it is probably divided into companies. So we might have a company A with 270 soldiers, company B with 270 soldiers, company C with 360 soldiers. I would take 90, a third, from the company A, 90, a third, from the company B, so it's proportional, and 120, a third, from the company C. And the reason is because I might be interested in this particular case not to deplete any particular company. So I'm going to have a portion from the first, portion from the second, portion from the third, equal portion in my eventual selection. That way I don't deplete any company, right? So that makes perfect reason. So this is called stratification. Population is first divided into stratas, layers, and then proportionally out of those layers we are taking the weight that we would like to have. In case of a political opinion, how was that in the last election? In case of this story about soldiers, then I guess I would just take 1/3 from each company. That is called stratified random sample. Now there is something called cluster random sample that sounds similar, but it isn't the same thing. Sometimes we are doing a cluster random sampling, and that means that we will first divide the population into clusters, into portions, and then we would at random take whole clusters. That could, for example, happen in a situation when you want to collect the political opinions, but or political preferences, but you don't have enough workers to do that. So you might divide the area where you want to get that opinion. You might want to divide that area into zip codes. and then you divide your workers to go into a particular zip code and just simply sort everything they can find in that zip code, right? But in that particular case, if you have 50 zip codes, you're not going to have enough people. So what you're going to do, you might at random select 5 of those zip codes and then get everything you can get out of those zip codes, those 5 that you selected. So you're randomly selecting the whole zip code. So which means, for example, Riverhead is a zip code. Maybe I will send nobody to Riverhead because it's not going to be in my selection of a cluster. So which means, again, population is divided into clusters. That might be a large number of clusters. And then first thing you do is you will select clusters at random. So for example, I have here in my story about the soldiers, we can talk about platoons, right? The battalion would have probably 9 platoons. So each platoon is 100 soldiers. So instead of going on any other way, I would just simply get numbers from 1 to 9, put them in a hat, and just draw 3. And I might decide, so this is like 1, 2, 3, and 9. And I say, okay, these guys are going on a mission, and the others would not. So which means I would select the whole platoons. Okay, this is with significantly more bias, right? I would have, in this particular situation, I would have platoons that were not selected, 6 of them, that no soldiers would leave the base, but there would be 3 platoons that would be completely selected. You might want to do that. That's in the particular situation I'm describing here. That might be the case. Why would you want to do that? I guess you probably want to keep the commanders of those platoon to be the commanders on the mission. So you're now going to have 3 of them, 1, 2, 3, and just you're going to appoint one of them to be the chief of the mission, and 2 of them to be assistants of his, and that will be easier to establish some kind of command there because they already have their soldiers, they know, so it'll be easier to work that way rather than selecting that random, in which case you have to have a whole command structure to reassemble for that particular mission, right? So I'm not saying I'm not really an expert on military or anything like that, but that could be the way to do it. So again, the difference between stratified random sample and cluster random sample is in stratified random sample you are dividing the population in strata, but then you're proportional taking from each of those layers. While in a cluster random sample, you divide the population in clusters, but then you're taking the whole clusters at random. So some clusters you're not taking, some clusters you're taking completely, right? So that's the difference. And the last thing about the sampling would be convenience random sample. I already have one today. When I was describing, I go to Walmart and parking lot, and I would find the mileage per gallon of the cars in the Walmart parking lot, and that of course would be convenience random sample because I would have there what is available to me, what is convenient to find, and that might not be representative if I'm talking about United States. The people that are in Comac Commons parking lot might be quite different than the cars that are there might be quite different than the cars that we would see on the road in all of the United States. So I would have certain bias. The bias would be because it's a local situation, so it might be a different than what I really wanted. But that is fairly often done, and it's the lowest quality of sample you can get. It's probably going to have it will probably have most bias you can find, and you probably would try to avoid that if you have. So in this particular story about these soldiers, if you have 900 soldiers and you want to select 300 to go on a particular dangerous mission, you could just simply ask for 300 volunteers. And you can immediately see that this would be a bias. You would sign up 300 people based on what they're going to volunteer for. So sort of a bias that would be here would be against cowards, right? Or into their benefits, right? They would not be volunteering, right? And maybe that's what you want. Maybe you don't want to send on that particular mission somebody who is really not into it. But that's probably, I guess, something that no military commander would want to do, unless it's a really, really tight situation in which he has to do something like that. Okay, so this is the types of a sample we collect. And again, let me point this out. A simple random sample is collected by a way of lottery, and that is the best type of a sample you could have. It should have the least amount of bias, and methodology itself is perfect, but the eventual sample might not be. For example, by some stroke of luck or coincidence, you could end up with a sample that is going to be made out of the first 300 people on a roll in alphabetic order, right? It's possible, but we don't expect that this kind of collection would be worse than the other four that I just mentioned. So again, let me repeat this. Simple random sample has the following properties. Every single entry item in the population has the same chance to be in your sample as any other. Any two have the same chance to be in your sample as any other two. And on you go, up to what the size of that would be. Any 300 would have the same chance to be in your sample as any other 300. If you can vouch for that, and that's really the way of lottery, that you can call what you have at the end a simple random sample. So that's the methodology we would expect to get something that is the closest to be a representative population. And I have to repeat this one more time. Eventual result or a sample might not be representative population, because no matter how hard you work on that, you might end up with something that would have intrinsic bias. And I said already, to avoid certain types of bias, we do the stratification, or we collect data by using stratified random sample, or sometimes we do that by using the cluster sample, right? I would hope you guys are going to be doing as soon as possible homework. So there is an introductory homework on some of these topics we talk about it today. And I wish you do that homework, and you will also have a small quiz about this. Quizzes in our grade allocations are extra credits, but there will be quite a few of them. So if you do more of them and you have more correct answers, you have more extra credits in your grade. And quizzes are graded than one and done, meaning you will have no repeated tries, while in the homework you can try any questions, you can work on any questions as many times as you like until you get the correct answer if you want to study. Okay, I will see you in the next lecture.